This video will demonstrate how to implement the map using a binary search tree. Hello, I'm James Helfrich. When I first started using the map, I was really confused with how that could be implemented. Every array I've ever used before used an integer as an index, which is just an offset from the first element in the collection. But a map can use anything for the key. How could that possibly work? This video will demonstrate how we can implement the map using a binary search tree. Okay, the first thing you have to realize about a map is how the client visualizes it. Let's say I have an int float map. So I'm going to say grades of 165 equals 94%. So my key is going to be 165 and my value will be 0.94. And if I say grades of 124 equals 97%, then my key is going to be 124 and my value be 0.97. Notice how that they're sorted. If I say grades equals 235, then this is going to go after 165. And now I have three keys, 124, 165, 235. We sort by keys, not by values. And the values are along for the ride, 0.89 in this case. When I add 213, 213 sorts before 235 and after 165. So I got to move it over. And then, of course, 246 goes on at the end. Now, the question is, how do we implement a map in such a way that I don't have to scoot things over and do too much work? Well, the answer is we're going to use a red-black balanced binary search tree. So let's do exactly the same problem again. So I'm going to say grades 165, and now I have a single node, and this node has a key, 165, and a value, which is 94%. Now, when I say 124, 124 goes to the left of 165. And since this is a red-black tree, it becomes red. When I say 235, 235 goes to the right of 165, and it is also red. Now, notice in each node, there's going to be two components. There's going to be the key, the integer 235, and the value 89% in this case. Now, when I go 213, 213 is to the right of 165 and to the left of 235, but I'm going to have to recolor my red-black tree. So 124 and 235 will become black, and 165 will become red, and then it'll become black again. And then I say 246, it goes to the right. Okay, so the super important thing to notice here is we have a BST, and every node is going to have two different components, the key and the value. And we always sort based on the key, and the value is just along for the ride. All right, we'll start with the class diagram of the map, the empty class diagram. We're going to have the usual default constructor, copy constructor, initializer list constructor. There are other constructors here like the move constructor, the iterator constructor, and others. And of course, we have the destructor. Now, containers have usually an assignment operator, a swap, a clear, a size, and an empty. This is something we expect. Now, what's unique to the map? They're going to have the square bracket operator where you can retrieve a value based on the key, the @ operator, which does the same thing except with error checking, and the erase operator, which will erase based on a key. Which means, of course, this class is going to have a template, in fact, two of them, both a key and a value. We're going to have an insert, which is going to insert a pair key value, which means I need to have a pair. And this pair is going to have two attributes, key and value, T1 and T2. And this is going to be related by association because I'm going to return a pair. I don't contain a pair. Let's dig into that pair a little bit more. That key and that value is going to be the T1 and the T2 of the pair, and they're related by composition, and there's going to be exactly one of each. Now, our map also is going to have a find based on the key, a begin, and an end, which means I need to have an iterator. And this iterator is a nested class within the map. Now, how are we going to implement the map? We're going to have a binary search tree. And so we need to have a binary search tree, and it's going to be a nested class within the map. And notice it has its own template because a binary search tree only knows about T's. It doesn't know about keys and values. Now, this BST is going to be a nested class within a map. It doesn't have to be, but it can be if you choose. And this map is related to the BST through association. The special type of association is composition because the map is going to create and destroy the BST. And how many BSTs will there be? Exactly one, even if the BST itself is empty. Now let's dig into that BST a little bit here. It's going to have a root, which is going to be a BNode, which means I need to have a BNode, which is a nested class within the map itself. And there's going to be an association between the BNode and the BST. Now, even though the BNode is a pointer, it's going to be composition because I'm creating and destroying the BNode. And how many BNodes are there going to be in my map? There's going to be many, 0 to unbounded, really. So even though I only have a pointer to a single BNode, I can access all the other BNodes through the pointers that are associated with it. Now the B node is going to have an attribute called data, which is going to be of type T, that BST is T. And so, but this T itself is actually going to be a pair of key values from the map. Now the BST and the B node do not know anything about keys and values. They only know about T's. But when we instantiate that BST, we're going to instantiate it as a key value pair. And so the BST is not going to be aware of it, but it's going to hold a collection of pairs. And how many pairs is it going to hold? Exactly one per B node. But since we're going to have many B nodes, that means there's going to be many pairs within the map itself. Now, there are a couple extra attributes. The main ones that we're going to talk about are going to be the pointer to left, pointer to right, and pointer to parent, which means they're going to be related to these by aggregation. In other words, if I create and destroy one B node, I'm not going to necessarily create and destroy other B nodes. Now, the numerosity gives me 0 to 3. 0 if I'm the only B node in the BST, there's the size of 1. 3 if I'm somewhere in the middle of the tree, and 1 and 2 if I'm on one of the edges. Okay, let's go back into the iterator. The iterator is going to have the standard constructor, the copy constructor, and the assignment operator. I'm also going to be able to create an iterator based on a given BST iterator. So I need to have a non-default constructor in there as well. I'm going to have the equals and not equals, which I need to have in order to iterate through. I'm going to have the increment. I'm also going to have a decrement, but I don't have space in here to cram that in. And I'm going to have a dereference. When I dereference the map iterator, I'm going to get a pair, which means this is also related by association to the pair class itself. Now, what's my member variable of my map iterator? It's going to be a BST iterator, which means I have to have a BST iterator. Now, this BST iterator is actually a map BST iterator, which is a nested class within the map. It's a public nested class. And the map iterator is going to be associated with a BST iterator. That association is composition because when I create a map iterator, I'm automatically going to create exactly one BST iterator. Therefore, my numerosity is 1. Okay, let's dig into that map BST iterator just one more time here. And this is going to have a single attribute, which is a pointer to a B node. And so this is going to be related to the map BST B node. And how's it going to be related? Well, I'm going to be related by association, but what kind of association? Aggregation. And this is important here because if I create and destroy an iterator, I do not necessarily create and destroy the associated B node. Therefore, it's just a pointer to it. And what's the numerosity? 0 if this is the null iterator and 1 if it is any other iterator. Whew, isn't that a complex class diagram? We can learn more about the map and the class diagram associated with it in the implementation section of the map chapter of the C++ data structures textbook.